Hey y'all, today we're going to start talking about single replacement reactions. Now, to be able to identify a single replacement reaction, we're going to be looking for basically we have an element, and that element is then going to react with an ionic compound. And when we do that, we're going to get a different element in return and a different ionic compound. Now, most of the time when we do this reaction, that ionic compound that we start with will be in solution. So it'll be a part of a solution dissolved in water, right? And so basically what you can see here is there's two different types of this, right? So first element we can have is a metal, we know that. And that metal we know will form a cation, right? And so since that metal forms a cation, right, it's going to want to come over here and it's going to kick this element out as from being there, and it's going to take its place as a part of that ionic compound. And the reason why it's able to do that is that some elements have a greater ability to donate electrons than other, right? It's called their activity. And so what we have here is a metal, much like think alkali metal, who really want to lose their electrons. And so basically what they can do is force their electrons on another metal and say, here, I don't want them, you take them. And so when that happens, they're forcing that other metal, that least reactive metal, to become go back and accept those electrons and become back to a normal elemental state. Then it becomes the cation that joins up with the anion to form the ionic compound. Likewise, we can kind of have the nonmetal come into play, right? So think fluorine. Fluorine, the most electronegative, really likes electrons. And so what it can do is actually come over here and it can basically take the electrons from another element, right? And when it takes that electron from the other element just goes back to its elemental form, and now that that element would become the anion and take part in the ionic compound, right? And so it's all about the flow of electrons when we look at the single replacement reactions. Which one are more likely to donate their electrons, or which ones are more likely to gain electrons? And so we get this. Now the big thing to remember, right, if we start with a metal, it's going to displace the cation, right? Because we know metals form cations. If we start with the nonmetal, it's going to displace the anion. So that's something to remember, right? Metals displace cations, nonmetals displace anions. Now I mentioned this activity series, okay? And so elements that have a higher activity are going to want to replace an element that that's already in the compound. For instance, if we look at the activity series, right, the big daddy is lithium. Lithium is the most active metal. And if lithium is there, it can replace anything below it, right? So elements that are higher up are able to displace elements that are lower down in a single replacement reaction. Same thing for our nonmetals. In here we just have our halogens, just to keep it simple. There, fluorine, that most electronegative, is going to be able to displace anything lower than it. So let's take a look at a couple examples of single replacement reactions, okay? And so now we have hydrochloric acid with magnesium, right? We've already seen this one, but let's take a look at it. Oop, sorry guys. Let's blow that up, right? So again, right, we have some hydrochloric acid, we throw some magnesium in there, and immediately we start to see those bubbles happening, right? So we have this lovely single replacement reaction, right? So we have magnesium, which is our metal, Mg, plus our hydrochloric acid. Now, I'm going to make that smaller. So we have our Mg, right, as a solid. We have our hydrochloric acid, HCl aqueous. And so what we see here is, if we think about this, here's my cation, H plus, here's my anion, Cl minus, magnesium's going to come in, it's going to kick out the hydrogen, and so we get hydrogen gas, which is our bubbles, and now we get plus Mg, and remember when Mg forms a cation, it forms a +2 cation, right? Chlorine has that -1, so we're going to get MgCl2, and that's going to be still in solution, okay? And so that would be the reaction that produces those bubbles. Now, if we go back to see, well, how is that possible? Well, here we see that we have magnesium. It's right here. Hydrogen's here. So magnesium is above hydrogen, and it's going to be able to replace it. So we see the bubbles start to form. Now, other reactions aren't quite as sexy. It's hard for you to see them. You have to be patient. So let's take a look at another one. Here we're going to take some copper, Cu, and we're going to take that copper and put it into a solution of silver nitrate, Ag, right? And let's see what happens. And so, so here's our silver nitrate. Here goes the copper in there. And really, it just doesn't look like anything's going on. But if we speed up the video, right, and we take a look at it, what we're going to start noticing is that copper starts to kind of change a little bit. And so we see that actually the copper is starting to get a little bit hairy. It's changing how we look at it. And we can say that it's looking like it's growing fuzzy, like it's growing fur. And what that actually is, as we kind of look at this, is that's the silver metal that's actually coming out of solution. And if we you can see, we speed it up a little bit, and we can see, and what we're also going to notice is that the solution is going to start to turn blue, because copper ions, when they go into solution, actually have a bluish color. So the solution starts to turn blue as the copper starts to go into solution, and basically we get this really fuzzy wire, and that fuzzy wire is just pure silver metal. So let's take a look at what that is going to be. Hopefully I can get this to go back down, right? And so now if we look, right, our copper, we look over here, and our copper, lo and behold, is here. Silver is here. So copper is above silver on the activity series, and so copper is able to displace that silver, and so we get some Ag as a solid. So we get Ag as that solid, right? Now CuNO3 2, so copper is going to form a +2 charge here, even though it's in a transition metal. I know that it's going to form that, right? And again, I didn't do it up here, but what we would have to do in both cases is we'd actually have to balance this reaction. So up there we would need a 2 there. Here we would need a 2 here and a 2 here to balance the reaction. And so there's that. Now, if we look at a reaction here where we have Cu plus HCl, right? Just by looking, we would probably predict that, oh, the copper is going to come in, it's the metal, it's going to displace the hydrogen, so we should get H2 plus CuCl2, right? So it should look like the magnesium metal there. But if we come back over here, we actually see that copper is below hydrogen, right? And so hydrogen's more active, and so copper is going to try to do that, and that's not going to happen because copper is less active. It doesn't have the ability to force its electrons, And so what we're actually going to see, or what we would predict, is that this reaction doesn't happen. We should see no reaction, right? And so here we have that example here, just quick. That is HCl, and we put some copper in the HCl, and it's spinning. All right, we're not going to wait for that. Basically what you would see is it would just sit in the copper because there would be no reaction. Okay, so again, just to recap, right? We have element plus a compound. It's going to give us an element plus a compound. Basically, we're trading out partners. If the metal or the nonmetal, that element is more reactive, then it's going to be able to replace the element in the compound. If it's less active, then we're not going to see a reaction happening. And that's where we have to refer to the activity series to see if that happens. All right, guys, I hope you have a great day. Peace, love, happiness. Thanks for playing.